Hello! Welcome to this HEEDS Technical Insights video, devoted to the topic of response dependencies. With this video, we assume that you are already familiar with the product called HEEDS and leveraging it to discover better designs faster. Today, we will showcase a newer feature within HEEDS called response dependencies. Added to the HEEDS MDO product in version 22.10, this feature was the first addition to the relationships banner to complement the original variable sum relationships. Like the variable sum relationships, response dependencies, when leveraged properly, can significantly increase search efficiency and/or uncover more innovative solutions faster. In this video, we will introduce the response dependency feature and its intended applicability, then look at a demonstration of how to utilize within the HEEDS product. Finally, we will look at some results showcasing the potential gains that can be found leveraging this solution. Let's get started. To begin, let's consider the value of leveraging relationships within a design space exploration study in HEEDS. While HEEDS search framework SHERPA is best in class, there will never be a replacement for you with your design and engineering knowledge. The premise of relationships in HEEDS are to capture that knowledge through a toolset to supplement the knowledge SHERPA attains. Rather than have SHERPA start learning from scratch, if we have preliminary knowledge or known rules that must be obeyed, we want to provide that information to SHERPA to help it kickstart the run or to ensure it is focusing on the pertinent areas of the design space. For example, relationships amongst variable definitions or in response goals, if known ahead of time, can be provided to SHERPA upfront to streamline the search process and satisfy your requirements. In the video today, we are going to focus exclusively on response dependencies. What do we mean by this concept? Here we are referring to how HEEDS associates variables with their impact on responses. In some instances, it may seem obvious to us as humans, but to HEEDS it needs to figure out which variables impact each response and which don't, unless we give HEEDS this information. Then additionally, HEEDS will figure out how the interactivity and degree of impact influences the overall performance against our goals. So, let us look at a multidisciplinary example. Here, we have three physical domains: a CAD tool, a finite element analysis, and computational fluid dynamics. For each domain, we have parameters associated with the given domain, and other parameters inherited from upstream domains or analyses, as we'll refer to them in the context of HEEDS. So for example, the CAD tool takes in geometric variables, while the FE tool takes in modeling variables specific to the FE analysis, while also being dependent on the upstream CAD design. Similarly, the CFD tool has modeling variables specific to it, as well as being dependent on the upstream CAD design. As a result of the process in the various solutions, we are interested in extracting the mass, stresses, and flow characteristics from the geometry, structural analysis, and fluids analysis respectively. Typically, we would set up this process and the associated variables and responses would be tagged in their respective files, and then HEEDS would investigate the impact of each variable on the respective responses. As noted, SHERPA would then efficiently optimize our problem against the goals we provided. However, in this case, we the engineers have more knowledge up front. Specifically, we know distinct response variable relationships a priori. We know for certain that the geometric variables are being passed directly into the geometry analysis and directly impact the mass. Our tagging tells us this. We could explicitly define this relationship in HEEDS. Similarly, due to the data transfer of the updated geometry to the structural and fluid simulations, we can also know beforehand that the geometric variables will also impact our stress and flow characteristic responses. We can define a relationship in HEEDS to enforce this. If no relationships are defined, default behavior, then HEEDS presumes they do exist and goes about determining which and how large each impacts the results for. So, there is not much difference here in that the geometric variables are presumed to impact each response. However, for our FE modeling parameters, they are known to only be pertinent for the responses from the structural analysis. In other words, they don't impact the mass or flow characteristics, for example. As such, we can define an explicit relationship to give this additional information to HEADS, in the hopes it saves HEADS time from having to figure that out itself. Likewise, the same is true that the CFD modeling parameters only impact the flow characteristics. And we can give this additional information to HEADS in the form of what we call a response dependency relationship. By using response dependency relationships, the user can prescribe known relationships to HEADS to save HEADS having to figure them out. This can increase efficiency, allowing the user to provide knowledge and input on the direction of the search, and can lead to better designs faster. It should be noted, however, that this feature should be used with caution. HEADS will use the defined relationships as truth, so if incorrect information is given, it will impact the search adversely. So if you don't know upfront the relationship between the response and the variables, don't use this feature. Let's take a look at an example where the response dependency relationship is vital to streamlining the search, and we're able to help SHERPA considerably in finding optimal solutions. We'll take a look at the example, and then see how we implement this in HEADS. Here we have an example where we are tasked with designing an IC engine, where there are typically goals and constraints at various RPMs. Each RPM here is considered a separate load case, or analysis model in HEADS. For example, as shown here, our two objectives are from set RPM conditions, while the constraints are applied over the entire RPM range, with individual requirements for each RPM being separate. Our variables include engine sizing characteristics and valve timings for both intake and exhaust, both of which have 11 variables each. Or in other words, we have one intake and one exhaust valve timing parameter for each RPM, or 22 timing variables in total. If we did not use relationships for this problem, HEADS would have to figure out for the objective the impact of each input variable on the performance of that response. In this case, that is unneeded repetition, as we know beforehand that for the intake and exhaust valve timing variables, only the 6,000 revolutions per minute parameters have any impact at all on the brake power at 6,000 revolutions per minute. So it is better for us to define this known response dependency up front, saving HEADS valuable simulation iterations to uncover this trend for itself. Let's see how we do this in HEADS. Now we are within the HEADS user interface, and we already have all of our variables and responses not only defined, but also tagged into our simulation models. We won't focus on the problem setup in detail, but solely focus here on the response dependency definition as the focus of this video. If we move to the Study tab, we notice the Relationships sub-tab that we may not be familiar with. If we select this sub-tab, we note we have three regions visible. In the top left is the Relationship Summary area, where the relationships are created. In the bottom left is a comments section where we can describe the intended purpose behind the relationship. And to the right is the Details area where the definition of the relationship is defined. In our case, we will add a response dependency. We can then give it a meaningful name. And we'll provide a comment to remind us later why the relationship was made and its intended purpose. To define the response dependency, we first select the relevant responses for the relationship. In our case, we'll select only the brake power response, valid for 6,000 revolutions per minute. Next, we define the variable relationships relative to that response. In our case, recall we know that all geometric parameters have a direct impact on the brake power. Since we've predefined groups for our parameters, an optional technique done here for convenience and organization, we see that the geometric parameters are easily accessible. We define their dependency accordingly. For the valve timing variables, we know that only the 6,000 revolutions per minute parameters are influential on the brake power at the same RPM, so we can define that dependency as well. Note that it is equally important to define the known fact that the other valve timing parameters, not coinciding with 6,000 revolutions per minute, do not impact the performance of the braking power. As such, this dependency must be prescribed as well. Doing so completes this particular response dependency relationship. With the brake power relationship fully defined to help us with one of our objectives, we can now similarly define an explicit relationship for our other objective. Again, here we know for certain the brake torque at 2000 revolutions per minute is independent of any timing variables except those related to 2000 revolutions per minute. Let's go set this up in HEDS as well. As before, we add a new relationship, ensuring we select response dependency as the type of relationship. We then provide a relevant name for the relationship, a comment to remind us or a colleague as to why the relationship exists. Next, we pick the response of interest. Finally, we designate all parameters as either having a known influence, designated with a yes, or not, designated with a no. Again, here we know for certain the brake torque at 2000 revolutions per minute is independent of any timing variables except those related to 2000 revolutions per minute, so there is no doubt about whether utilization of responses is appropriate or not. Similarly, for our constraints which are applied independently for each RPM, we can explicitly define relationships for each RPM, as shown here for the brake torque at 1000 revolutions per minute. Likewise, we can define similar response dependencies for all of our other constraints, since each is dependent solely on the engine sizing parameters and the timing for the respective RPM. That being said, what are the types of performance gains we might expect in using the relationships feature compared with if we didn't? Let's take a look at an example that contrasts the two scenarios. To demonstrate the power of the response dependency feature, we will look at a computational fluid dynamics example. Specifically, we will look at an example that from the practical sense most will relate to. We have an automobile where we are looking to maximize the performance of an HVAC system. Notably, we'd like to get as much airflow to key passenger locations in the vehicle to maximize the heating or cooling experience for passengers. As such, we are presented with the question, how to best orient the vent deflectors to maximize the velocity field at 4 target zones. We define 4 target surfaces within the vehicle and have 8 geometric parameters which vary the angles of the 4 deflectors for the HVAC system, horizontal and vertical deflector positioning respectively. We want to maximize flow to be concentrated around the driver's eye and elbow, as well as the passenger's eye and elbow. The 4 deflectors each map to a specific target as follows. The driver's eye target should be facilitated from the driver outer deflector, the driver's elbow target from the driver inner deflector, the passenger eye target from the passenger inner deflector, and the passenger elbow target from the passenger outer deflector. Here, we are using SimCenter Star CCM Plus to model the deflector geometry in a parametric fashion as well as the computational fluid dynamics. SimCenter Star CCM Plus 17.02 was used to model the HVAC system for a Maserati Ghibli. With a mesh size of 2.65 million cells, the CFD simulation takes about 45 minutes utilizing 64 compute cores on an HPC. As such, as it pertains to design space exploration, efficiency is key here. Given the fact that there are 4 distinct regions/zones for mass flow rate achievement, and each is governed primarily by 2 independent variables respectively, 2 angular variables for each deflector, this is a prime candidate to leverage response dependencies on. The question of course remains, however, what type of efficiency gains can be attained using this feature? To find out, we did a direct comparison with HEDS and the SHERPA search framework on this problem, comparing the solution speed while leveraging the response dependencies with that when no dependencies were used. For each scenario, 120 evaluations were given to SHERPA as its search budget. As rationale, with 8 parameters, we expect that 120 evaluations is a realistic budget for SHERPA when not leveraging response dependencies. We allowed SHERPA to run 6 designs in parallel with SimCenter Star CCM Plus on 64 cores each, resulting in 13 hours and 45 minutes of turnaround time for each design space exploration. For completeness, we ran each scenario 10 times with varying random seeds between runs to reduce the impact of the starting search cycle population on the conclusions. So in total, each scenario was run 10 times, resulting in 20 design space explorations in total being conducted for comparative purposes. Within HEADS, we can review the problem setup. We see our SimCenter Star CCM Plus portal configured for running our 6 designs in parallel on our HPC. We have our 8 variables defined as continuous with an increment of 0.1. These variables are tagged as global parameters directly in SimCenter Star CCM Plus using the portal. For outputs, we've tagged 4 responses corresponding to the weighted average velocity at the 4 locations of interest, referred here to as DI, PO, DO, and PI, corresponding with the driver inner, passenger outer, driver outer, and passenger inner deflectors respectively, as shown prior. Likewise, we are extracting the computed minimum distance to the target. We can review the goal of the study. We have set SHERPA to a weighted sum strategy with 4 weighted objectives for maximizing the weighted average velocity. Each objective has its normalizing factor prescribed as 1 to avoid biasing of objectives based on the baseline performance. Additionally, the minimum jet distances were set as constraints to ensure guidance to all 4 zones/regions of importance. For the regular SHERPA run without response dependencies, that completes the setup review. Let us now look, however, at the setup of the response dependencies for that scenario. We see that 4 response dependencies have been set up, 1 for each location. At each location, the respective responses for that location, weighted average velocity and minimum jets distance to target, are defined with the same dependency, being an explicit yes dependency to their 2 respective variables and an explicit no dependency to the other 6 irrelevant parameters to the respective responses. Next, let's look at the results. Here we have selected one run where 200 evaluations were utilized on this problem to demonstrate the general improvement that can be attained on this problem. In looking at the objective history plot, we can see that all 4 objectives can be improved considerably in their goal of matching the target. If we alter to only look at feasible designs instead of all designs, this becomes a bit clearer. Due to the 4 objectives, it can still be a bit difficult to quickly interpret the results in this case when considering our goal to assess the quality of solution found by different methods. Notably, SHERPA, with and without response dependencies, across 10x optimization runs each. As such, we will be utilizing the calculated performance as our frame of measurement for comparative purposes. The performance history plot, as shown here, is the driving metric HEADS seeks to maximize during an optimization. The final reported value will be leveraged in our comparisons momentarily as the frame of reference for the quality of solution found by HEADS. As a reminder, the performance function is calculated using the following formula by HEADS, auto-created based upon the optimization problem statement prescribed. This parallel plot provides us an idea of the design landscape for this problem and the anticipated best design variable combinations for our deflector angles. Shown here is a comparison between the baseline configuration and that of the best design. Clearly, the optimized design will lead to a dramatically improved cooling or heating experience for the passengers. Let's now alter our focus to the performance gains observed when utilizing response dependencies on this problem. Recall the methodology for comparison discussed earlier. Next, we will compare the results from 10 separate optimizations with SHERPA using response dependencies versus 10 separate optimizations with SHERPA where no response dependencies are leveraged. The difference between the 10 optimizations in each case is the random seed utilized, which influences the starting population for the optimization. Shown here are the results from the comparison. A box and whisker plot is utilized to summarize the results with the mean, individual data points, and the spread encapsulated. Here the data is representative of the final HEADS performance number attained. We've superimposed the baseline performance as reference. It should be noted that whether or not response dependencies are leveraged, SHERPA finds a great solution robustly for this problem relative to the starting design. However, it is also clear that the response dependency optimizations found considerably better solutions within the budget allowed, 120 design evaluations in this case, on this problem. If we add a table next to the chart to summarize the scenario, it becomes even more apparent that the response dependencies helped us find a better overall solution on average. Additionally, when looking amongst the optimized designs from all 10 optimizations for each scenario, it is also clear that the best performing optimization where response dependencies were leveraged is significantly better than the best when they weren't. In fact, the best without response dependencies is less than the average of when the response dependencies were used. Similarly, the worst of the 10 optimizations for each scenario showcases that the response dependency worst solution is much better than the worst of the non-response dependency runs. And in fact, not that different from the best optimized solution when no response dependencies were used. So the conclusion here is that leveraging response dependencies on this problem has clear advantages in discovering better designs. But what about the speed to finding innovative solutions? If we choose a set threshold for comparison, here we choose a performance value of 33 or greater, then we can ascertain the speed in achieving that threshold during the optimization. If we compare the percentage of optimizations with each technique that surpassed the threshold, having a best performance greater than 33, we see that all 10 optimizations with the response dependencies defined surpass the threshold. Whereas, when the response dependencies are not used, only 5 of the 10 optimizations reach the threshold. For those optimizations that reached a performance value of 33, we can compare how long it took to reach that given performance. With no response dependencies defined, it took 110 designs on average to reach a performance of 33, again noting that only 5 of them reached the threshold at all. While the optimizations with response dependencies on average only took 67 designs to achieve a performance of 33. As a result, for those optimizations that achieved a performance of 33 or greater, the optimizations with the response dependencies were 39% faster in achieving the threshold. This case study, therefore, hopefully provides you with an idea as to the potential advantages to using response dependencies on your problems as appropriate. This concludes this Technical Insights video. We hope that leveraging response dependencies, you can discover better designs even faster. Thank you for watching.